Welcome to the fourth part of Lesson 4. In this final part of the lesson, we will conclude our discussions of aromatic compounds by examining the reactivity of aromatic side chains. We will then conclude the lesson by looking at a few examples of aromatic chemistry in the context of organic synthesis, showcasing how the principles we've learned can be applied to create substituted aromatic compounds, using directing effects to control the outcomes of the reactions. Let's go to the next page and get started. In organic chemistry, the reactivity of side chains on arenes, also known as aromatic compounds, play a crucial role in various chemical transformations. The side chains, typically alkyl groups attached to the aromatic ring, can undergo several types of reactions, including oxidation, reduction, and substitution. These reactions are significant because they allow for the modification and functionalization of aromatic compounds, making them valuable intermediates in the synthesis of complex molecules. They can also help us change the directing effects of the side chain, providing the chemist with additional strategic control when planning a synthesis. For example, let's consider the reaction known as benzylic oxidation. Recall that the term benzylic refers to a CH group that is directly attached to a benzene ring. Benzylic oxidation therefore refers to oxidizing this benzylic position. For example, alkyl group side chains can be oxidized to benzoic acid. This process requires strong oxidizing agents such as potassium permanganate, which has the formula KMnO4, and sodium dichromate, which has the formula Na2Cr2O7. A crucial point to remember is that a CH bond must be present at the benzylic position, which is the carbon atom directly adjacent to the aromatic ring. Let's consider an example of this reaction. The benzylic oxidation of toluene, also known as methylbenzene. When treated with potassium permanganate, in acidic conditions, this reaction converts toluene into benzoic acid. Notice that the directing effects are switched as a result of this transformation. Specifically, the methyl group, an ortho-para-director, is converted to a carboxylic acid group, which is a meta-director. Let's look at another example. Consider the following tri-substituted benzene derivative. The name for this compound is 1-tert-butyl-4-isopropyl-2-methylbenzene. Looking at the structure, we can see that there are three different alkyl groups attached to the benzene ring: a tert-butyl group, an isopropyl group, and a methyl group. When we subject this compound to strong oxidizing conditions, like potassium permanganate or sodium dichromate, the reaction targets the benzylic hydrogens. In this molecule, the tert-butyl group does not have any benzylic hydrogens, so this alkyl group remains unchanged. The isopropyl group and the methyl group, however, do have benzylic hydrogens, making them both susceptible to oxidation. During the oxidation process, the isopropyl group and the methyl group are both converted into carboxylic acid groups. The tert-butyl group remains unaffected due to the lack of benzylic hydrogens. As a result, the final product of this oxidation reaction is a benzene ring with a tert-butyl group, two carboxylic acid groups, where the isopropyl and methyl groups were, and no change to the aromatic ring itself. This transformation illustrates the selective nature of side chain oxidation, emphasizing the importance of benzylic hydrogens for the reaction to proceed. It also shows how the presence of different alkyl groups on the same aromatic ring can lead to varied outcomes depending on their structure and the availability of benzylic hydrogens. Now that we have looked at the oxidation of benzylic alkyl groups, let's go to the next page and look at the reduction of nitrobenzene. Nitro groups attached to a benzene ring can be effectively reduced to amine using catalytic hydrogenation conditions, which we learned earlier are an effective means for reducing an alkene or alkyne into an alkane. These same conditions can be used to reduce nitroarenes. This reaction is significant in organic synthesis, as it allows the transformation of a nitro group, which is a strongly electron-withdrawing and deactivating group, into an amine group, which is electron donating and activating. In catalytic hydrogenation, the benzene compound with the nitro group is exposed to hydrogen gas in the presence of a metal catalyst, typically palladium on carbon or platinum. The metal catalyst facilitates the addition of hydrogen atoms to the nitro group. Catalytic hydrogenation is a highly efficient and selective method for reducing nitro groups, often yielding products of high purity. This reaction is widely used in the synthesis of pharmaceuticals, dyes, and other aromatic amines, demonstrating its importance in industrial and laboratory settings. By reducing the nitro group to an amine group, we can significantly alter the reactivity and electronic properties of the benzene ring, enabling further functionalization and application in various chemical processes. The nitro group, being strongly electron withdrawing, is both deactivating and a meta-director. By converting the nitro group into an amino group, the benzene ring becomes activated by the non-bonding electron pair on nitrogen. This amino group is electron donating and an ortho-para director, which enhances the ring's reactivity and directs subsequent substitutions to the ortho and para positions. That concludes our discussions on reactions of substituents on the benzene ring. Let's go to the next page and look at some examples for how we can use these reactions, and others we have learned in this lesson, to solve a few multi-step synthesis problems. For the first synthesis example, let's look at the conversion of benzene into 1-amino-3-chlorobenzene. Pause the video and take a few moments to plan out the reactions necessary to accomplish this transformation. When you unpause the video, we will review the solution. Go ahead and pause the video. Ready to look at the solution? Alright, let's take a look. The first step in solving this type of problem is to identify the substituents attached, and determine the reactions necessary for their attachment. The chloro group can be attached by using the chlorination reaction, which occurs by electrophilic aromatic substitution, EAS. This reaction substitutes one of the benzene hydrogen atoms with a chlorine atom. We do not, however, have an EAS reaction that replaces a hydrogen with an amino group. The amino group can be generated by the reduction of a nitro group. Therefore, the problem requires that we prepare a synthetic intermediate, 3-nitro-1-chlorobenzene, as a direct precursor to the final product. This analysis, in which we work backward from the target compound to its precursors, is called retrosynthetic analysis, and is a key tool used in organic synthesis. But we haven't yet solved the problem. We still need to show how to prepare this synthetic intermediate. Notice that the two groups present, the nitro and chloro groups, each have their own directing effects. The nitro group is meta-directing, but the chloro group is an ortho/para director. How does this impact our synthesis? Notice that the two substituents are in a meta-orientation. This means that whatever group we put on first must be a meta-director. Otherwise, the second group would get attached to the para position. This means that the immediate precursor to this disubstituted intermediate must be nitrobenzene, since the nitro group is the meta-director. So what are the series of steps needed to convert benzene into the product? Let's turn our retrosynthesis into a forward synthetic plan. First, we will nitrate the benzene ring, using the EAS reaction conditions for nitration, specifically nitric acid and sulfuric acid. This produces nitrobenzene. We can then rely upon the meta-directing properties of the nitro group to direct the next reaction, chlorination, which requires us to treat our material with chlorine in the presence of a Lewis acid catalyst, aluminum chloride. With the chlorine installed in the meta position, it is time for the final step in the synthesis, catalytic hydrogenation. This reaction converts the nitro group to an amino group by reduction. Let's go to the next page and try one more example. For the second synthesis example, let's look at the conversion of benzene into 4-tert-butyl benzoic acid. Pause the video and take a few moments to plan out the reactions necessary to accomplish this transformation. When you unpause the video, we will review the solution. Go ahead and pause the video now. Ready to look at the solution? Alright, let's take a look. If we apply the technique of retrosynthesis to this example, we can see that the carboxylic acid group implies that this final product was prepared by the benzylic oxidation of a precursor that had an alkyl group in place of the carboxyl group. We can choose any alkyl group for this location, as long as it is sp3 hybridized and has at least one hydrogen atom. I will choose a methyl group. Now we need to focus on preparing this synthetic intermediate, which has two alkyl groups in a para orientation relative to one another. This is favorable because both groups are ortho/para directors. The question then becomes, which group should we attach first? Recall that tert-butyl groups are strongly activating and have a tendency to promote overalkylation during the Friedel-Crafts reaction. If we attach the methyl group first, this can limit the amount of overalkylation because the molecule would already have a group in the para position once the alkylation occurs. The forward synthesis therefore starts with the Friedel-Crafts alkylation of benzene using methyl chloride and a Lewis acid catalyst. The second Friedel-Crafts alkylation attaches the tert-butyl group. Finally, treatment with potassium permanganate or sodium dichromate causes benzylic oxidation of the benzylic methyl group to generate the final carboxylic acid product. This concludes the final part of Lesson 4. In the next lesson, we will take a brief break from learning reactions and revisit the concept of isomerism, this time with a focus on the fascinating concept of stereoisomerism. See you in the next lesson.